Hello, welcome back to the channel. So let's do one question on splitting these complex expressions into multiple components by only using partial fractions. So before watching this video, if you have not watched my previous video on partial fractions, on the introduction of partial fractions, I would highly suggest you to first watch that video in order to get the full context of this video. So again, in this expression, you see the same case, you have factored out terms in the denominator. So that would give you a very good idea that it might be easier for you to use partial fractions in order to split this expression into different individual components such that you know the integral of those individual components. But in this question, we just have to simplify this expression into the general form of the partial fractions decompositions. And in this question, it's also not necessary to calculate the coefficients in this case. The coefficients, by coefficients, we mean the values of capital A, capital B, and capital C, whatever constants we'll have on the right hand side. But before doing that, a very important thing about using partial fractions is that whatever factored out terms you have in the denominator, they should definitely be in the form where they cannot be simplified or factorized further. Because in this case, you see an x square minus 1 whole square, and you also know that x square minus 1 can be factorized further, right? X square minus 1 can be written as x plus 1, x minus 1, right? So this is definitely not a term which is not factorized to the simplest form possible. So that is why before using partial fractions on this expression, this whole expression will have to factorize the denominator to the simplest extent possible. So now let's write the expression first. Our expression is x cubed plus 3 divided by x square minus 1 whole square and x square plus 1 in the denominator, right? And you also see this thing that x square plus 1 cannot be factorized further, right? Because it does not have real roots. So now we'll first factorize this expression over here to the simplest extent possible, which would be simply x cubed plus 3 upon x plus 1 whole square, x minus 1 whole square, and x square plus 1, right? I just opened this x square minus 1 term. So x square minus 1 is equal to x plus 1 times x minus 1, and then you have a square term as well outside. So you'll take x plus 1 whole square times x minus 1 whole square, right? So now you have this expression over here in the denominator. You see two square terms over here and one quadratic expression in the denominator, right? So what you'll do is you'll use this chart, and whatever we discussed in the last video, we'll implement the concepts that we learned in the previous video. So now first let's take the x plus 1 whole square term. So now we know that in this case, whenever we have an x minus a to the whole square term, we simplify those expressions as, so first you take the term which is in the square, you put that in the denominator and have a constant in the numerator, and then you square that term and then do the same thing with another constant, right? So in this case, what you'll do is, for x plus 1 whole square, this expression will be a upon x plus 1 plus b upon x plus 1 whole square, right? And similarly, this would be the case for x minus 1 whole square as well. So for x minus 1 square, you'll have c upon x minus 1 plus d upon x minus 1 whole square, right? So now we are done with this x plus 1 whole square. We're also done with x minus 1 whole square. The only thing that is left is this quadratic expression over here. And as we discussed in the previous video, whenever you have a quadratic expression in the denominator which cannot be factorized further, what you do is you take the quadratic expression in the denominator, and then in the numerator you have a polynomial of 1 degree lesser than the denominator in this case. So the quadratic expression in this case. And since we know that the quadratic expression is of degree 2, so whatever numerator will have degree 1, right? So that is why in the numerator you have capital BX plus capital C in this case. So again we'll do the same thing for this expression. For x square plus 1 term, we will have EX plus F upon x square plus 1 in this case, right? Using the same thing that we covered in the previous video. So this expression would be easily simplified to this expression over here. And then you can easily solve for these constants by equating the numerator that you'll get with the numerator in the original expression. Don't worry, we'll do another question based on that concept as well. But this video was specifically about splitting up our complex integral expressions into different multiple individual components such that calculating the integral of those multiple individual components is easier than calculating the integral of the whole complex expression in this case. So now you can clearly see in this case that if you were to calculate the integral of this expression, it would have been a lot more easier if you were calculating the integral of this whole expression over here, right? Because these are very common terms for your integral forms, right? So that's it for this video. Again, feel free to comment down on this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.